Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll review what we learned in week 7. It's all about area under the curve, which includes definite integrals. So we'll start with this problem. I want to find the area under this curve between x equals 0 and x equals 1. So I'm finding this area shaded in yellow. So what we can do is we can estimate this area by using shapes like rectangles or trapeziums. So here I'm going to use 4 left rectangles to estimate the area. So left rectangles means that each rectangle, its height, it hits the curve on the left, as opposed to if it was a right rectangle, like this one here, would hit the curve on the right, this middle rectangle there. So you're probably thinking, oh, there's only 3 rectangles there. Well, that's because this first rectangle would have no height, because it would hit the graph here at the origin. So what we do is we make each rectangle have the same width, the same distance along the x-axis. So if there are 4 of them between x equals 0 and x equals 1, the width of each rectangle is 0.25. So the height of each rectangle is determined by the y value of the function. So this point here would be 0.25. So the height of this rectangle, or the length, would be f of 0.25. And similarly, the height of this rectangle here is f of 0.5. This is f of 0.75. And of course, the first rectangle here, it has area 0 because f of 0 is 0. So putting each of these values into the function, I get this, f of 0, f of 0.25, f 0.5, and f of 0.75, and I just rounded them all to 4 decimal places. And so putting that in the calculator, I get about 0.4707. So that is my estimate of the area under the curve. So that's using 4 left rectangles. So instead of rectangles, we could use one trapezium. So using a trapezium, I start at the first point, I want to end up here, and I draw a trapezium. Now, because the first point here is at the origin, this trapezium actually turns into a triangle. So the formula for the area of a trapezium is area equals perpendicular height on 2 times the sum of the 2 parallel sides. It's just in this case that one of the 2 parallel sides has length equal to 0. Here, A is like 0. B, this length here, is f of 1, which is 5. And h, the perpendicular height from 0 to 1, is just 1. And so the area we get using the trapezium is 2.5 units squared. So in the case of 4 left rectangles, this was a reasonable estimate, you know. The first couple were below, so they were a little less than the area they were supposed to cover, but this last one here was an overshoot. It covered a bit more area than it was supposed to. The trapezium in this case probably wasn't a good estimate, and that's why we have quite a discrepancy between answers. So sometimes rectangles are better, sometimes trapezium's better. Sometimes each of these gives a good estimate for the area, and sometimes they don't. But the reason we need these numerical approximations is there are functions that we just can't integrate. But it turns out we can integrate this one. It turns out the exact area in yellow is just the definite integral of this. So definite integrals have numbers here, and your final answer is a number. We still use this integral symbol because we're finding the antiderivative. So the antiderivative of x to the power of 4, I increase the power by 1, divide by the new power. And for x, I increase the power by 1 and divide by the new power. I don't add a c when I'm doing a definite integral because the c's would cancel out. So what I do to get the answer for this is I evaluate it between 0 and 1. I evaluate the antiderivative at this point, evaluate the antiderivative at that point, and then subtract them. So substituting in x equals 1 into this expression here, I just get 1/5 plus a half. And substituting in 0 to this, I would get 0. So I have when x equals 1 minus when x equals 0. And x equals 0 just makes the whole thing equal 0. So a half plus a fifth is just 0.7. So the exact area in yellow is actually 0.7. You can see in this case, the rectangles were a much better job than the trapezium, but that's not always the case. So sometimes we need trapeziums or rectangles to numerically approximate the area under a curve because we can't always integrate functions. Sometimes we can even find the area when we don't have the function. But if we can integrate the function, we use a definite integral, and that will give us the exact area under the curve. All right, I need to make a point about signed areas now. So let's say I wanted to find the area bound by this curve and the x-axis between x equals -3 and x equals 3. So this is what the curve looks like. Now in this one, apologies that it's probably not clear from my drawing, this area and this area have the same magnitude. They're the same. But because this area is above the x-axis, when I do a definite integral, it would give me a positive number, but this area is below the x-axis. So if I did a definite integral from here to here, it would give me a negative number. So if I were to find the area between the curve and the x-axis of this one here, I would use the definite integral from -3 to 3. The problem is I get 0. So that doesn't make any sense, really, because the area between the curve and the x-axis is clearly not 0. The reason the answer is 0 is because this area and this area are the same number but different signs. They would cancel out each other. So this, unfortunately, makes things a bit more confusing. When you need to find the area under the curve using a definite integral, you need to know when the curve is above and when it's below the x-axis, because any area below the x-axis will be negative. So to find where a curve is above or below the x-axis, there's no harm with you first graphing it on your graphics calculator. So how then do I use integration to find the area between the curve and the x-axis? Well, this is what I'm going to do. I'm going to split it up into two integrals. I'm going to find this area and this area separately. So this area here will be given by the integral from -3 to 0 of my function here. And this area here will be the integral from 0 to 3. We always put the lower number, the smaller number, on the bottom of the integral. So if I were to add these together, I would get this. I would just get 0. So what I have to do, because this area here is negative, because this is a negative number, I need to subtract it and turn it into a positive. So if the area here was like -4, I'm just going to pretend the area is +4. So I can add these together. I won't get 0. I will get this area plus this area. So by the way, dx just tells us that we're integrating with respect to x, that x is the variable. So to integrate this, we use the same rules we have been doing for integration for a while. Increase the power by 1, divide by the new power. Increase the power by 1 and divide by the new power. So I'm going to evaluate this between -3 and 0. And then this one here will be the same. It'll be x to the power of 4 over 4 minus 9x squared on 2. But I'm going to evaluate it between 0 and 3, and I'm going to subtract this answer here from this answer. So doing this and putting it on my calculator, I should get 81 on 4 plus 81 on 4. So this one here gives me 81 on 4. This one here gives me 81 on 4. So adding them together, I get 40.5 units squared. That is this area here plus this area here. So that's what I mean by signed areas. You have to account for whether the area is positive or negative, and you need to do a separate integral for the regions of the curve that are below the x-axis. To find when the curve is below the x-axis, you can use a graphics calculator. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.